Hello dear friends and welcome to another electronics video. Today we will be discussing operational amplifiers. So operational amplifiers can be found in most of the electronic circuits and most of modern electronic circuits. They are fairly used, also integrated in bigger integrated circuits or standalone design. Their main function is to amplify a signal, a input signal. So here in this picture here, we have the schematic for a operational amplifier. It's a rough schematic. They have the differential amplifier here, the differential input, which means that we have two types of inputs. We have an inverting input and a non-inverting input. These two values, as you can see here, tend to be the same, have the same voltage level. So this point here is 0.7 volts, let's say the voltage drop between the base and emitter for Q1 transistor, and it's also 0.7 volts from the base of Q2 transistor here. So they tend to have the same voltage level here. The input stage is one of the most important and most defining stages of an operational amplifier because this will determine if you need, for example, a floating ground, or you need a or you can use this with a single supply stage. So in this case, for example, we are using two um, voltage levels for supplying this component. In a later part of the video, we will be discussing how you can reduce these two levels and, for example, in this case, use only a 24 volt um, a 24 volt supply, and how and what changes are required for this component to be able to function correctly at this voltage level. Okay, so we've defined that we need an inverting input and a non-inverting input. These values are fairly at the same voltage level. We also have an output. Here the differential pair is going to the final stage here where they are the amplification is done so that you can have a bigger output and not influence the differential pair on the input. And the output will fluctuate between the two voltage levels, of course, minus the voltage drop on the two transistors on the output here. Simplified, the schematic looks the following. So it's a triangle where we have a inverting, we have a non-inverting input, which is the plus, and we have an inverting input, which is the minus. So these two inputs. We also have two lines for supply, the positive and the negative supply, and of course the output value. From amplification point of view, most operational amplifiers have very high amplifications. So we are discussing here thousands, even tens of thousands of times the input voltage. So this means that the amplification, of course, is the output here divided by the input. So how much do we amplify the input value? And it's defined as being A, and of course is the amplification is A times the difference between these two voltages here. Okay, there are a couple of golden rules for designing operational amplifiers. So the golden rules state how we as engineers, electrical engineers, we look at the component. So the first one is infinite input impedance. So we assume that the operational amplifier has infinite impedance here. So no current is drawn into this input here. This means that we are not influencing the circuit connected to the operational amplifier by any means. The second golden rule is infinite amplification in open loop. So without a feedback from the output to the to the inverting input, the component shall have a very high amplification. As we've discussed, this can be in the thousands and even tens of thousands times bigger. And the third rule is the values of V plus, which is the non-inverting input, and V minus, which is the inverting input, are equal if feedback loop is used. So these values are equal. If we do not have a feedback loop, any very small difference between these values will push the output to go high. So this is why, because we have this very high amplification, we always need to have a feedback loop. And the feedback loop is connected uh, to the inverting input. If the feedback loop is connected to the non-inverting input, this is usually done for oscillators and Schmitt triggers, which we will discuss in detail in further operational amplifier videos, because I want to go quite in depth regarding this component. It's quite important. Okay, going forward, just that we get a bit into the electronic side of the circuit. So here we have a non-inverting amplifier. So this means that the sine wave here will be repeated on the output in the same phase. There will be no phase difference between, if this goes up, the output goes up. Okay, and for in order to calculate this circuit, what would be the amplification for the circuit? Because we want to create rules for different circuits to better know uh, quite fast and quite easy what is the amplification of the circuit. So we go back to the rule where we define that V plus equals V minus. So if these values are equal, this means that the input is connected here. So the difference between the input and the output is just a voltage divider here. So we have output, which is the output voltage is divided by Rg and Rf, and it's equal to the input voltage. So V plus is a voltage divider, which is Rg over Rf plus Rg. More information about the voltage divider can be found in the basic electronics resistors video. And this is time V out, or the output voltage. Going forward, we are just moving all this here, and the V plus value, the non-inverting voltage level, we're just moving under V out. So V out over V plus, or V input, is the inverse of this fraction here, which is Rf plus Rg divided by Rg. And of course, if we split this fraction, we get Rg divided by Rg plus Rf divided by Rg. So this means that the amplification for the circuit is 1 plus Rf divided by Rg. So let's take a simple example, because this will clarify a bit the electronics. We want to create an amplifier that has an amplification of, let's say, 7. We want to have a voltage level here, and we want to have times 7 the voltage level on the input. So this is quite easy. We already know, so 7 would be equal to 1 plus Rf divided by Rg. So it's clear that Rf divided by Rg has to be equal to 6. Okay, so we can take, for example, we can fix our G at 10 kilo ohms and our F will be 6 times bigger. So it would be 60 kilo ohms here. Just to make things simpler, I have highlighted here what is the amplification value for this circuit. Going forward, let's discuss a bit the inverting amplifier. So the inverting amplifier difference is the input for the non-inverting goes into the non-inverting pin, and for the inverting amplifier it goes into the inverting pin. The feedback is the same. It's negative feedback always because we're amplifying a circuit. We're not creating a oscillator or a Schmitt trigger with this circuit. So in this case, we have we are going to use the second rule, in which we say that the voltage level on the input on the non-inverting input and the one on the non-inverting input are the same. So this means that the current flowing through here is equal to the current going through here. Quite simple. So this means that the current going through Rn is minus the current going through Rf here. So how do we calculate the current going through these two resistors? So it's quite simple because we defined that these values, the voltage level for minus and the voltage level for plus, are equal. So this means that everything is connected here to ground. So we can assume that the input, so here it's ground, so it's going to be the current going through here is voltage equals resistance times current. So current equals voltage divided by resistance. So the current for this, or voltage, the input voltage divided by the Rin is equal to the output voltage divided by Rf, or RFB feedback. In this case, we have an amplification, so Vin divided by Rn equals Vout divided by R feedback. So this means that if we move Vn from here to here and R feedback on the other side, then Vout divided by Vn, which is the amplification, is a voltage. It's a divider between R feedback and Rn. So the amplification is the, the value of this division here. So let's say we want to do the same thing as for the other non-inverting amplifier, and we want to amplify this value by 7. Okay, so this means that the voltage, this division here must be equal to 7. So for example, if we fix this at 10 kilo ohms, then this has to be 7 times bigger, which is 70 kilo ohms. So here we have a 70 kilo ohm resistor, and here we would have um, a 10 kilo ohm resistor. Okay, going forward, let us also discuss a bit about the single supply. So till now, as we have discussed, we are using these dual supplies here, plus 12 volts and minus 12 volts. And because the input for the operational amplifier that we are going to use today, which is the LM741, it's a very standard operational amplifier. There are much better operational amplifiers for audio applications, which have a much better behavior. So let's take this component, and this on the input, it has PNP transistors here. And these PNP transistors, they need a voltage level for the ground reference. So for the single supply, we would need a reference voltage level for this ground level. so that it can fluctuate between plus and between the maximum value and the lowest value of the component. So in this case, what we are using is the 741. We are supplying everything at 20 volts. We have the same circuit as we had here for the non-inverting amplifier. And then we are we have the same rule as before. So the rule for this circuit was that for the non-inverting one was that the amplification value is 1 plus the feedback resistor, which is R5 divided by R6. So in this case, it's 1 plus 3, and this means that the total amplification is 4 for the circuit. Okay. Let us now go to the second part of the video where we do a small simulation, and in the final part we will go a bit through a small operational amplifier challenge. It's quite important that we do and we perform electronic let's say tasks and electronic design activities. So here we will discuss a bit about the challenge. So going forward, let us open LT Spice and create a new schematic. So for the schematic, we are going to use the component LM741. If you do not have this component in your library, please watch the LT Spice 741 video where I discuss how you can add this component to your library. Okay, so we have added the component. The next step is to supply the component. And first, let's start with a non-inverting amplifier, and let's build the circuit for this. So, as we said, we will need a differential supply. So we are going here back, going to the voltage source, and placing two voltage sources here, which we will put a value of 10 volts for each of them and another 10 volts value, and these will supply the circuit. One other thing that we have to do here is to place the ground between these power supplies, because in this case, this being a differential power supply, this terminal here, and I'm going to annotate this so just that I make it clear, this would be plus VCC and is equal to 10 volts, to plus 10 volts here. And on the other side here, we will take the um, negative terminal from the power supply, and here this is minus VEE, which is minus 10 volts. The minus 10 volts is a voltage level reference compared to the ground reference here. Okay, and let us first connect these. So I'm going to connect this to the supply, to the negative supply, and here we have the circuit. Now we would need something to drive the circuit, so I'm going to place another voltage source, and here I'm going to change it. So right-clicking this and going to advanced, you have multiple selection options for this. So let us go with a sine wave, and let's say that we want to add a signal, let's say 1 volt, and we want to 1 volt and let's put 4 kilohertz. 4 kilohertz is usually in audio spectrum, so it's a good frequency to test an operational amplifier for audio applications. So let us connect the ground to the power supply, and let's connect it to the non-inverting input. Great. So the last thing that we have to do is to create the feedback network. And as we've defined here, so for an amplification of 7, we need to have, so the amplification, total amplification is 7. If we remove 1, so we extract 1, this means that 6 has to be the value for this division here. So this means that we have to add 2 resistors here. Let me uh, place the 2 resistors. One we will rotate so that we can have a better and much clearer schematic. I really love clear schematics. Let's place the first one at 10 kilo and the second one at 60 kilo ohms. Okay, and let's connect everything together. So the feedback network to the inverting input. Okay, and this is the output. Great. One last thing we need to add is the ground reference here so that we can connect the ground to the feedback. So our circuit is complete. We have the output, we have the feedback resistors that are going into the non-inverting to the inverting input. We have a beautiful 1 volt 4 kilo ohm sine wave. So this should be fixed. Okay, let us click on the run button here and let's put like 10 milliseconds for a transient analysis here. Okay, let us look at the input. So this is the input. The value goes from 1 volt from minus 1 volt to 1 volt and back again. And let's look at the output. So here we see that our 1 volt input transformed into a 7 volt output level. Great. This is great. So the circuit is working quite well. Also, you can see that, and this is quite important, that the signals are in phase. So when when the input goes up, the output goes also up. Okay, let us then go forward and create a non-inverting inverting input design. So for the inverting input design, we are going to let me do a copy here, just that we take all the components. So Control C to copy the components from one side to another, because I would like to do a parallel between the two designs. So I'm just copying the LM741. I'm going to copy one of the feedback resistor, the second feedback resistor, the ground for the resistor, just to make it a bit faster and that we don't have to draw it again. Okay, and let us connect the second operational amplifier to the same voltage levels here. So, okay, let me do this again. I missed it a bit. Okay. Oh, okay, and let me connect it here. And for the negative voltage level, let me move also this resistor from here so that we don't interfere in the traces here. We don't want to accidentally connect the minus to the feedback network. Okay, and now let's move these a bit lower because these are the feedback resistors, and we are great. One last thing, I'm going to copy the sine wave input and I'm going to place it here. Okay, so this is our signal input, and let us again remember the structure for the amplifier. So for the inverting amplifier, we need a input resistor and a feedback resistor. Great. So let's take one of the resistors, like the 10 kilo ohm resistor, place it here, rotate it so that it's in series here, and we would need also a feedback resistor, which is placed here. Okay. And one last thing, we have to connect the inverting input to ground. So let us go back here, and I'm going to connect the non-inverting input to ground. So I'm going to take a ground connection, just move it a bit. Uh, it, I'm going to keep it this way. Okay, and I'm going to connect it to the non-inverting input. And then for the inverting input, I'm going to connect the resistor, going to move it a bit above to be aligned. I really love to see really good designs when it comes to the schematic organization, not to have a lot of overlapping between components and traces, just to make things a bit clearer, and yeah, not accidentally uh, do some overlapping and connections. Okay, so we are back here and we are going to modify. So we want to get a 7 times amplification on the input sine wave. So this means that according to our calculations, the amplification is the difference between our feedback and our in. And this means that uh, our feedback has to be 7 times bigger than our in to get a 7 times amplification. So we have to update this to 70 kilo ohms. Okay, and we are good to go. Let us run the simulation. Here we have the input signal, we have the non-inverting value, and here we have the inverting value. Maybe it would make a bit sense that I zoom in a bit so you can see, and also let me delete the non-inverting one because we know this is done correctly. Okay, so now we see that when the signal goes to minus, the output goes high, and also the output is 7 volts, so it's 7 times the 1 volt input signal. And when the input goes high, the output goes low, times 7, of course. So this is the main difference between a inverting and non-inverting um, amplifier, operational amplifier. And let's look at the two waves. So these are dephased. So when one goes up, the other one goes down. So it's they are perfectly dephased here. Okay, great. The last thing that we said that we would be discussing today is the same circuit but without using a differential supply. So it's quite hard to find a differential supply for your circuit, and yeah, it's usually it will kind of bulk the circuit a bit. So let's do the same design but with one supply here. So let's take or maybe I can copy some of these values. So I'm going to copy the operational amplifier. I'm going to copy the signal, the sine signal for the input, and I'm going to copy one power supply and the ground for the power supply here. Okay, so let's connect the single supply here. So we are connecting to the V plus, and the the minus value is V minus, or the negative voltage. We're going to connect it to the lowest voltage level that we have, which is ground. And so this is great. One other thing that we have to do, so we've connected this. Let's connect the supply. Now, one thing that is quite um, important here is you will never get, so here if we connect this to the input, you will see only half of the wave. Usually it's good to have a isolation between the input signal and the input into your operational amplifier. This is why I'm going to place a capacitor here just to create a voltage level half of the voltage supply. So this is just that here we have the middle value between the power supplies plus and the ground. So let me take this component, no, the component, and rotate it like this. Okay. Let us give it like a 10 microfarad capacitance. And what we're going to do is create the middle point. So now we're working to create the middle point at which the operational amplifier will receive the signal. So to create a middle point from 10 volts, we have to do a divider by 2. So here we would need 5 volts. So this is quite simple. We just put here 10 kilo ohms with a 10 kilo ohms resistance, and it's done. It's quite simple. More details, as I said, regarding voltage divider and also for the capacitor, for the resistance at a certain frequency, you can find in the capacitor basic electronics capacitor video and basic electronics resistor video. Okay. Now we are just connecting the middle point here, the 5-volt point, and now we're just connecting this to the non-inverting input. Great. So last thing that we have to do is to get to create the feedback network here. So this is quite easily done. We've already built 2 feedback networks here. So we said that we will build this non-inverting value. So I'm going to place 2 resistors here. One, I'm going to rotate it here, and let us calculate the values. So we're saying that we want to amplify this 7 times the input. So this means that we're going to use the same values as here. The amplification is 1 plus R8 divided by R7. So as we used previously, we're going to put here 60 kilo ohms and here 10 kilo ohms. So here I'm going to write, I'm going to write 60 kilo ohms on the feedback, and here another 10 kilo ohms. Okay. So this seems to be quite done, but not precisely done. There is only one topic here. If we connect this point from this resistor to ground, as we are having here, the circuit would not work because the ground for us is at half of the power supply here. So in order to create this correct voltage level here, we are going to use a capacitor, and I'm going to use a quite large one, 100 microfarad capacitor here. Ideally, this would be ceramic if you want to build the actual circuit, and connect everything together. Okay. And let's go in retrospect and look at the circuit. So we are having a sine wave going through a 10 microfarad capacitor here, just to scale it between the inputs. So we're taking the 1 volt peak to peak volt signal, we're scaling it to 5 volts or half of the power supply. Here we can change the power supply, you can make it, and we have to change it. You can make it whatever, of course not exceeding the maximum supply voltage for the component, but here this value will vary with the power supply, and this means that you will always be centered in the middle of the value of the power supply here. And Okay, so we are taking the signal going through the capacitor to the DC value here, which is half of the supply. We're having the feedback network here. So the feedback network, as we've discussed, is the amplification is 1 plus the division of these two components. And we have a C2 capacitor here, which is mandatory because we're using ground as a reference, and we need a voltage reference here for the operational amplifier in order to create the amplification. Okay, this is great. One one last thing that we have to do is to change the value for the power supply, because we here we have 1 volt peak to peak. So this is 2 volts. If we're amplifying 2 volts times 7, it's 14 volts, and we're supplying everything at 10 volts. This will be kind of squished here. We don't want this. Let us put here a 20-volt power supply, just that we have enough margin for the circuit to function. And let's click run and see how the circuit is looking. So here you can see the signal. Let me delete the other signals so that we are in. So this is the input signal here that we are amplifying, and this signal is then passed through the capacitor here, and you can see that the capacitor creates this voltage level here of half of the supply voltage. So it's 20 divided in two. So the signal is then um, has a DC voltage offset of 10 volts. Okay, let me delete this. And then you can see the beautiful amplification here, and everything goes from 10 to 17 volts, and then from from 10 to 3 volts here. So this would be the non-inverting this would be the non-inverting single supply operational amplifier. One last thing before we go into the challenge. If we went with the 10 volts, the operational amplifier cannot create the voltage levels here. So it's going to kind of cut the signal or saturate the operational amplifier. This is just that you know how a saturated, yeah, this is how the amplifier is trying to amplify the circuit, but it's kind of reached the maximum it can go. And of course, it cannot go to 10 volts because, as we've discussed here, it has also the driving circuits here. It also has a here sometimes you will find current mirrors, so it would not be able to reach the 12 volts in this case, and in our case the 10 volts, and it's quite squished here. What we can do is, in order to make the circuit look better, we can change the values for this resistor. So let's not amplify it that much. Let's, for example, amplify it by 3 times, and then let's put here a 20 kilo ohm. So how do we amplify this 3 times? So we have 1 plus R8 divided by R7, which is 2. So this is by 3 times. And here the circuit looks much better. It doesn't saturate, and it's looking quite well. It's non-inverting input. It's scaled to the voltage level of the middle level here of the power supply at 5 volts, because we have these two R5 and R6 resistors. Okay, let's do a zoom to fit so we can get an overview. Great. Last topic of the video is our small operational amplifier challenge. So each week I would like to do some challenges for the design videos, just that we keep up with the know-how that we have, and yeah, it's always important. One last thing before we move into the challenge. If you want for this power supply, if you want, for example, to use a 20-volt power supply here, we have a great video for a charge pump that you can supply all the amplifier to a 9-volt battery, and you can get quite high voltage levels. We for that video, I think it was 27 volts. You can see it on our channel. It's a good video. Just that you can imagine that you can create quite high voltage levels with a small battery, and yeah, it's a fun and interesting circuit to have a charge pump supplying an operational amplifier. And maybe in a future video we will do like a headphone amplifier, and even in an audio 8 ohm speaker amplifier. That would be quite interesting video to do. So coming back to the challenge, so this week's challenge is first of all a non-inverting amplifier, operational amplifier circuit with amplification equal to 10 with a dual supply, a inverting amplifier circuit with amplification of 5 and a dual supply, a non-inverting circuit with an amplification of 4 and a single supply. And for the supply levels, you can choose whatever supply level you consider fit. And for the fourth challenge is a inverting operational amplifier with amplification of 3, but with a single supply. Okay. Please tell me in the comments if you had fun building and creating these challenge circuits, and if you have any questions, feel free to contact me through comments, even directly write me. I am really passionate about electronics, and I like to share my passion with other electronics enthusiasts. So that being said, I would like to wish everybody a great day. Thank you for your time. Hope you find this video interesting, and don't forget to like and subscribe. Goodbye.